Hi, I am Muhammad Rabiul Islam. In this slide, I describe the answer based on advanced semiconductor physics, that midterm 1, 2, and 3. Here I explain midterm 1. Draw Fermi level. Draw Fermi level distribution function in intrinsic silicon at temperature 300 Kelvin and 400 Kelvin. Uh, this energy level, this represent energy level that's in electron volt, and this represent the probability of Fermi direct distribution function. The probability 1 represent the mm, it's represent the valence band, and probability 0 represent the conduction band, and the middle position of this is zero point 0.5. That's zero point 0.5 probability, half of total probability. Here is band gap, this the maximum 1.1 for silicon, and uh, we know silicon has energy band gap 1.1 electron volt, and uh, its a Fermi level exist in half of total band gap. That means 0.55 electron volt. That's this position. Here actually Fermi level is not a physical guideline, it's a mathematical guideline, but conduction band and valence band is a physical guideline here. Initially when temperature is at 0 Kelvin, then the electron in valence band is stable, and the conduction band electron is 0. When we increase temperature like 300 Kelvin, then some of electron come from valence band towards to conduction band for gain, and for gain some energy. When this come from valence band to conduction band, this occupied this place, occupied this place. Here it's it means to the concentration of electron in conduction band. And when temperature 400K, it's represent this red color graph. When increased temperature, the electron from valence band to conduction band uh, comes more, that's occupied more place in here. It's more than the 300K temperature. That's represents black graph. Here we see that at 300K the occupied electron in conduction band is low, but the 400 Kelvin temperature, the occupied electron in conduction band is large than a 300K. That's why the 400K the graph is sharp than 300K. Here calculate the probability at 0.01 electron volt above and below Fermi level at 300 Kelvin and 400 Kelvin. There first of all, we if it's valence band, its conduction band, are the Fermi level here, I think. They calculate the probability. Its probability, first of all, 0.01 above. In this case, we think it's here 0.0 electron volt above Fermi level. In this condition, at 300 K, and the probability what's happen. We know Fermi level. Here probability is 0.510. When when the when Fermi level up to here in this here at 300K, the probability we calculate here, we get reference level is 0 electron volt. We think it's reference here to minus 0.55 and another 0.5 is here, total 1.1. It's I think it's a 0 electron volt. It's up to 0 1.1. In this way we EF is reference energy level 0 electron volt, and E is the above of reference. That's why that means here is probability. Here is probability what happened in this case. Okay. When we at temperature 300K, we get K into T is 0.0259 electron volt. Its exponential is 1.49. Fermi direct, we get 0.4. That's things here we get 0.4 probability to get electron. At 400K, in this condition, what happened? Here at same condition we get a probability to get probability of electron, that's 0.42. We get here to a electron probability here is 0.42. In below condition, the new one, it's a reference reference level. We think below the here below the reference level, we take minus 0.1 electron volt. In this at 3K and 300K and 400K, the at temperature the probability, that's here we get a 0.6. That's here is the probability of electron is 0.6. At temperature 400K we increase temperature 400K, that's the probability, that is 0.57. In this case we increase temperature, that's from the valence band electron is more excited at 400 Kelvin temperature. That's Fermi level here is a decrease, but at same temperature here is I think a more probability here is 0.57. that means electron go towards the conduction band. More electron goes conduction band to valence band in this condition, but it's go less. Fermi level is below zero point 0.2 electron volt EC. Draw Fermi direct distribution function in silicon at 300 Kelvin temperature and 400 Kelvin temperature. Here it's a valence band, it's a conduction band, it's Fermi level here. We think the Fermi level is below EC. That means it's totally 1.1 electron volt. That means uh, it's below. That means here below the zero point 0.2 of conduction band. Here is Fermi level. But intrinsic semiconductor Fermi level is situated in middle position. Here we get in this case Fermi level shift from it's for intrinsic silicon. It's our condition here. That's why our in this case we say that the Fermi level is here near to the conduction band. The energy the Fermi level towards to conduction band here. That means it's the silicon. This means it's a n-type semiconductor. N-type semiconductor, and the Fermi level close to that. That close means the occupied electron is here, conduction band. That's when temperature 300 K, it's black, and here the Fermi level is 0.9 electron volt here. The Fermi level shifted towards the conduction band. Shifted towards the conduction band. Here shifted to the conduction band. That's called n-type semiconductor. Here the occupied electron at 300 K is less than occupied electron at 400 Kelvin temperature. It's here here we can see the 400 K temperature. The n-type semiconductor graph is sharp than 300 Kelvin temperature. Question: Fermi level is 0.2 electron volt above valence band. Draw Fermi direct distribution function at temperature 300 Kelvin and 400 Kelvin. It's a valence band, it's conduction band, it's a Fermi level of intrinsic semiconductor. But in our question the Fermi level is situated here near to the valence band, near to the valence band. Here 300 K here show this graph and 400 K show this graph. It means the p-type semiconductor Fermi level near to the conduction band. At 300 Kelvin temperature, the electron from here to here is going. It's going, the here is Fermi here is probability is 1. Here is probability 0, that's why here is 0.5 is Fermi level. Here in this way the Fermi level, and when a temperature is 4 Kelvin, 400 Kelvin, there's the electron is grow up here to here, the large, then this is shift here to here, little bit up, little bit up in Fermi level at 0.2 electron volt above to the valence band. Here we can see at the temperature its Fermi level is here, this this here the occupied electron is here, is T 300 Kelvin and T 400 Kelvin. That's it's for p-type materials. Here it's a Fermi level, energy level, and it's a probability. Explain what is the difference between Fermi distribution pattern at 300 Kelvin and 400 Kelvin. Figures 1, 2 and 3 show the Fermi distribution at 400K is sharper than 300K, indicate that increase in temperature Fermi level is sharper than at low temperature. As a result, conduction band as electron density is high and Fermi level is present close to the conduction band. High electron density, it's high electron density to the electron conduction dense is n-type materials. Here midterm 2, silicon semiconductor is doped with it's called donor impurities 10 to the 6 and 10 to the power 18 per cube centimeter. N-type dopant find Fermi levels and calculate hole concentration at 300K temperature and 400K. Response here, and the donor concentration, but donor impurities 10 to the 6 at the Kelvin, approximately concentration of electron in conduction band is equal to the donor impurities. We know for silicon, intrinsic silicon, it's 1 at the 10 to the power 10. We know the concentration of electron and concentration of hole equal to the value of intrinsic Ni. Then from it gets the hole density of valence band is 2.25 into 10 to the power 4 centimeter cube. From this we get the here is EF is a reference it's a Fermi level, its EF is Fermi level and EFI is intrinsic Fermi level. The difference is 0.347 electron volt. It means EV EC, it's EFI and it's a intrinsic reference. It's mean EF minus EFI equal 0.347 electron volt. This means I think here is Fermi level, this is reference, it's that value. Here the donor impurity is 10 to the power 18 and temperature is 300 Kelvin. Here approximately the concentration of electron of conduction band is equal to the donor impurities. That's why here we get the difference, the reference electron intrinsic Fermi level and the difference between Fermi level and intrinsic Fermi level is 0.46. It means here like EV and EC. It's intrinsic Fermi level, and that's why it's ND. Donor impurity is more. It's N-type materials. That is I think here the difference is that's value. That means it's the Fermi level near to the conduction band. The increase of ND donor impurities, the Fermi level is close to the conduction band. The opposite is 10 to the donor impurities is 10 to the 6 when temperature increased 400 K. All thing is good in this case. EV EC and it's a reference intrinsic Fermi level. Here it's also n-type semiconductor. That means in this case it's here this Fermi level and intrinsic Fermi level difference. That means it's near to the conduction band. It's near to the conduction band. Here we think increase in this case increase at the same 10 to the power 18 and temperature is T 400 Kelvin. In this case EV is the conduction band EFI here, and it's I think in this case Fermi level is overlap with conduction band, and the difference between EFI and EF is 0.62 electron volt. That means the occupied electron density in conduction band is high. In this case donor impurity is 10 to the power 6 at a temperature 300 K. This represent this black graph. Donor impurity is 10 to the power 8 temperature 300 K. This represent red graph. Donor impurity is 10 to the power 6 temperature 400 K, and this represent this blue color. And donor impurity is 10 to the power 8 temperature 400 K. This represent this graph. Now when the donor impurity is 10 to the 10 to the power 6 at temperature 300K. In this case, this graph, it's a probability. It's here the Fermi here we think it's a conduction band, it's a valence band in band gap, not probability. It's a probability. It's band gap. In this case, when we apply 10 to the power 6 impurities, here it's conduction band. Then here a middle here this case the electron from in this case the Fermi level is here and conduction band here. When we drop impurities in Fermi level, when we temperature, then here electron Fermi level to conduction band. Here is create a temporary positive charge. When we applied or impose the impurities tend to the same impurities when we increase temperature, then we get the graph is higher than before. Its Fermi level is towards the conduction band. That means increasing temperature, same impurities, donor impurities, that's shift the Fermi level towards the conduction band. It means the conduction band electron density is high, increase of temperature. When we impose donor impurities 10 to the power 18 at temperature 300K, it's red. It's also near to the conduction band. When same amounts of donor impurities at temperature 400K, that's overlap conduction band. That's why same amount of donor impurities increase temperature, the electron occupied this conduction band is higher. That's why the Fermi level is near and close or overlap the conduction band. In this graph, it's a summary. Explain what is the difference between Fermi distribution pattern at 300 Kelvin and 400 Kelvin. Figure the Fermi distribution at temperature 400K, which is sharper than 300K, demonstrating that Fermi level increase sharply with temperature. The Fermi level near to the conduction band, and conduction band it has a high electron density. As a result, the conduction band has a high probability. That's one. Here the midterm. In the course, we taught many of things about semiconductor, basic Fermi level, why Fermi. At this moment, I tell the position of Fermi level. What is its It's n-type, p-type, or intrinsic semiconductor. At this moment, I understand that. Here we know the Fermi level is mathematical guideline, which is imaginary, and conduction band and valence band is physical guideline, not mathematical guideline. And we know about a Fermi Dirac distribution function probability for intrinsic silicon, the relation between Fermi Dirac distribution temperature in various condition, the significance of Fermi Dirac the function of drift current, the concentration of electron and holes, that's important role increase of current, the relationship between Fermi distribution probability and energy level at equilibrium temperature, the main difference between Fermi distribution and Maxwell-Boltzmann approximation, how to determine the position of Fermi level band gap, deeply know the Fermi level position for intrinsic and extrinsic semiconductor, determination of densities, state of semiconduction band and valence band. What is the difference between Fermi-Dirac equation 1 and Fermi-Dirac equation 2? Doping process of n-type and p-type semiconductor with impurities. How to select impurity based on energy level of the impurities table provide Professor J.O. Park. A depletion layer mechanism of p-n junction. How to make compensate silicon. From this lecture, it's help to us understand about semiconductor more details that I cannot before know about semiconductor. The most significant thing I lecture from nowadays, I characterize the semiconductor to look up the Fermi level, which was not possible for me before this lecture. The valence band probability 1 and conduction probability 0 at present when the Fermi level is situated middle of energy band gap. It indicates the intrinsic semiconductor. It is an n-type semiconductor with high conduction band electron concentration because the Fermi level is present close to the conduction band. And p-type semiconductor, the high concentration of valence band holes, Fermi level close to the valence band. Fermi distribution function is more important to understand physical significance of band gap. Uh, at this moment, I understand more precisely and identify the n-type, p-type, extrinsic, intrinsic semiconductor to see the Fermi level position in materials. Thanks to all.